by 1932, physics had got a relatively consistent picture of matter and its interactions. We had a dense nucleus that contained almost all the mass of the atom, that was made up of protons and neutrons, and surrounding that was a cloud of negatively charged electrons, and the whole system was bound together by photons, and we knew that when electrons moved between energy levels in the atom, they either absorbed or emitted photons. Now, there were still a few niggling problems with that we've discussed. What was holding together all the positively charged protons in the nucleus, and what was the cause of the strange energies that were observed for the electron in a beta decay. However, before we deal with that, we need to discuss how we described the atom itself. And that was using Schrödinger's famous equation. Now, the Schrödinger equation is basically a statement of conservation of energy. You have a kinetic energy term, you add to it a potential energy term, and you put that equal to the total energy of the system. Now, if you look at the kinetic energy term and you break it down into its operator form, then you see that it's the momentum operator squared divided by 2 times the mass. And there is the problem, because that relationship, p squared over 2m, relies on a classical energy mass momentum relationship. It's essentially the classical kinetic energy, a half mv squared. And that isn't going to work when you're dealing with high energy particles. So instead of the classical relationship, you need to switch to using Einstein's relativistic energy mass momentum relationship. The problem is people have tried to use that and come up with a wave equation that used it, but when you do that, because you have energy squared, you end up with both positive and negative energy solutions. And you can't, because you're coming up with a fundamental equation that is describing fundamental physics, you can't, every solution of that equation has to be something that exists. Otherwise, you've made a mistake somewhere. And the problem is these negative energy solutions seem to make no physical sense. Now, in 1928, that changed when a young British physicist named Dirac came up with an interpretation that worked for these negative energy solutions. Now, we're not going to deal with the mathematical details here, we're going to leave that for later in the course, but for the moment what we can say is that Dirac showed that these negative energy solutions was a new type of matter. It was antimatter, and that doubled the number of particles. He immediately predicted that as well as electrons, protons and neutrons, there were anti-electrons, anti-neutrons and anti-protons. And it wasn't until 1933 that the first of these particles, the anti-electron or positron, was discovered by a American physicist named Anderson, who was looking at cosmic rays and saw a positively charged particle with the same mass as an electron. And that immediately doubled the number of particles overnight and inadvertently made Star Trek possible. At least the old versions of Star Trek, not Star Trek Discovery, which seems to run on magic mushrooms. So, now we had doubled the number of particles. The next problem that fell to physicists was what held together the nucleus. Now, after the discovery of antimatter by Anderson, it was only 1 year later that the Japanese physicist Yukawa came up with a model to explain the strong nuclear force. And what he did, what his sort of main idea was that he gave the force carriers of his strong force a mass. And essentially what that mass did was it limited the range of the force. Right? It acted as essentially a damping on the particles being emitted, and so you ended up with a very restricted range for the force that could explain why the nucleus was limited in size and was very, very dense. Now, to transmit this force, he had to introduce some additional particles, and in order to make his theory work, he had to give these particles a mass of about 6 times less than a proton. And so these were lighter than a proton or a neutron, which had roughly the same mass, and heavier than an electron, so they were in the middle, and so he called these particles mesons. Now, only a few years later, in 1937, there was much excitement because in cosmic rays, again, these are detectors that were flown, in this case, in a balloon, detected something that became known as the mu meson. And this mu meson had a mass that was a little bit on the light side, but was about the right sort of energy range, and seemed to be one of the mesons that Yukawa had predicted. But there was a problem. When people looked at these mu mesons, they found that they were very penetrating. They would go through large distances of matter before they stopped, and this wasn't what was expected from a meson from Yukawa's model, because these mesons would be strongly binding. They would interact very strongly with the nucleus. Now, admittedly, they had to get close to a nucleus to interact, but if they got within that distance, they were almost guaranteed to interact. And so you could predict how far they'd go in matter, and it was a lot shorter than the distance that these mu mesons were going. And it took a few years to find out the solution for that. In fact, 10 years. It wasn't until 1947 that a British physicist, Cecil Powell, again using these balloon experiments, studying cosmic ray interactions, discovered a slightly higher mass particle that was called the pi meson that decayed into the mu meson. And this higher mass particle, this pi meson, or pion as we call them now, actually had the right properties. It could not go very far in matter before it interacted, and was very consistent with the predictions of Yukawa from just over 10 years previously. So at this point, we had found the particles that transmitted the nuclear force and bound the protons and neutrons together into the nucleus. So we'd solved now the mystery of the strong nuclear force, but at the expense of introducing this strange mu meson. But before we could solve what this mu meson was, we needed to look at beta decay. Now, if you remember, the problem we had with beta decay is we had a parent nucleus decaying into a daughter nucleus and an electron, so there seemed to be only 2 decay products. And given that there's a fixed energy difference between the two, there's only one way to assign that energy to the kinetic energy of the outgoing particles in a way that conserves both momentum and energy. So the problem we had was that when you looked at the electron's energy, it had a range of values, and nobody could explain why. The Danish physicist Niels Bohr was famously ready to throw in the towel of conservation of energy and just decide that energy was no longer conserved in beta decays. It wasn't the first time, I think, or indeed the last time, that he was willing to give up this. Fortunately, the cooler head of German physicist Wolfgang Pauli prevailed, and he suggested that the solution to this problem was to add in an extra neutral particle that escaped the decay without being seen. Now, with this additional neutral particle, you now have 3 particles in the final state, and there are multiple ways you can now share the energy between the 3 decay products such that energy and momentum are conserved. And in fact, what Pauli showed was that you would get a spectrum that looked similar to the spectrum that was observed, providing the neutral particle was light. Unfortunately, he chose the name neutron for that particle, and only the following year Chadwick discovered the neutron as we now know it, the big massive particle that's bound in the atomic nucleus. And in fact, at that point Pauli left the picture, and it was up to the Italian physicist Enrico Fermi to develop a full working model of nuclear beta decay, which involved a very, very light, in fact, in his models, massless neutral particle, and being Italian, he called it the neutrino, for little neutral one. Now, the neutrino we know now, in fact, it does have a mass. And the reason we know it has a mass is because about 20 odd years ago, we discovered that neutrinos can oscillate, and the only way that they can oscillate is if they have masses. So we know the neutrino has a mass, but its mass is so insanely light that we have not yet been able to measure it. We know it's not zero, but it's so small that we haven't actually yet managed to see it. And in fact, the interesting thing is the way that we try to measure the mass of the neutrino is we look at nuclear beta decay, and we look at the very end point of the spectrum. And if the neutrino has a mass, that end point of the electron spectrum will be changed because some of the mass, some of the energy has to go then into the mass of the neutrino. And so that's how we actually do direct searches for neutrino masses. However, it's all very well to have a theory, and Fermi's theory was very convincing, but until you've got experimental data to prove that that theory is correct, nobody is going to believe it. And the problem with Fermi's theory was that to show it was correct, you had to detect the neutrino. And that was a very, very difficult thing to do. Fermi's neutrinos could travel through light years thicknesses of ordinary matter before they had a reasonable chance of interacting. And obviously, building detectors on the scale of light years was completely impossible. So instead, what you have to do is you need to go for an incredibly intense source of neutrinos, so that even if your odds of a neutrino interacting in your now reasonable size detector may be 1 in a trillion or even far less than that, if you have enough neutrinos passing through, you will still have enough interactions that you can see and provide evidence for the neutrino. And so that, to discover those, it relied on an experiment that was conducted in the 1950s. Now, finding a sufficiently intense source of neutrinos was not easy. The first experiments to try and find the neutrino, in fact, involved putting a detector near a nuclear bomb test. Now, a nuclear bomb, when it detonates, produces an enormously intense burst of neutrinos. However, the burst doesn't last very long, and in fact, neither does your detector, so that didn't prove to be a particularly good solution. The better solution was discovered in 1950 when Cowan and Rines put their detector near a nuclear reactor. Now, nuclear reactors work on fission, and when a heavy nucleus like uranium splits into two daughter nuclei, the two daughter nuclei are very neutron rich and immediately undergo large amounts of beta decay. And that beta decay produces a flux of anti-electron neutrinos. Now, what they did was they had a very ingenious design that could unambiguously pick up the signal of an anti-electron neutrino interacting with a tank of water. And what they did was they placed two tanks of water that were doped with a cadmium salt. And cadmium is a very good neutron absorber. Now, inverse beta decay is when an anti-electron neutrino comes in and strikes a proton, and of course water has lots of protons. When that happens, the proton is converted into a neutron, and a positron, anti-electron, is emitted. And this gives you two signals. The first signal comes from the positron that very rapidly annihilates with electrons in the water and produces two gamma rays. And what Cowan and Rines did was that they put detectors above and below each tank, and when the positron annihilates, it produces a photon, and some of those annihilations will have a photon going up into the top detector and a photon going down into the lower detector, and so you see coincident photons at exactly the same time in the detectors above and below the tank, and that's the first part of your signal. The second part of your signal comes from the neutron that's produced. And this bounces around in the water for a little while until it encounters a cadmium nucleus, where it gets absorbed and causes the cadmium nucleus then to emit a single gamma ray, but that gamma ray comes a few microseconds after the 2 gamma rays from your positron annihilation. So they have this delayed coincidence of a signal both above and below the tank in their detectors, followed by a few microseconds later with a single photon that would either go up or down, and so you end up with this sort of threefold coincidence: 2 photons at the same time, 1 photon a few microseconds later, and that was sufficient for them to prove unambiguously that the neutrino existed. They saw this signal in their detector, and it was unambiguous proof that the neutrino existed. The mystery of beta decay had been solved, and a new type of particle had been discovered. Now, having found the neutrino for beta decay and solved that mystery, we were now primed with all the information we needed to tackle the mysterious mu meson. Now, what physicists did was they looked at the production and decay of this mysterious mu meson. Now, when you looked at the production, you could see a pi meson, which was one of Yukawa's mesons, decaying into a mu meson, but there was a kink in the track. And what that told you was there had to be some invisible extra particle that wasn't being picked up by the detectors when that happened, that was being emitted in order to conserve momentum. And of course the obvious candidate there was to have it be a neutrino. And more detailed studies of these decays showed that the muon neutrino was produced with a fixed energy if the pion had decayed at rest, and so what this showed was that this was a 2-body decay. There was only one missing invisible particle because you had a fixed energy for the mu meson. Now, looking at the other end of the track, people saw that the mu meson decayed into an electron. And again, that was the only visible decay product. There was a kink, so there clearly had to be a neutral particle being emitted that wasn't picked up by the detector. But the electron from the mu meson decay had the same problem as the electron from beta decay. You start with a single particle, the mu meson, you end up with one visible particle, the electron, and that one visible particle doesn't have a fixed energy. It had a range of energies just like the electron from beta decay. And that meant that it had to be a 3-body decay. So when the mu meson decayed, it didn't just emit one invisible particle, it had to emit 2 or more. And the prevailing theories at the time were that since they knew of the existence of neutrinos, what they theorized was that the mu meson, in fact, was not a meson at all. It wasn't behaving like one of Yukawa's mesons, it wasn't interacting well with matter like it should be doing, and it was producing neutrinos when it was produced and when it decayed. In fact, it was behaving like an electron. And in fact, that changed the name. It was no longer thought of as a meson, but instead it was thought of as the heavy cousin to the electron, and its name changed to the muon. So now we got this new theory that suggested that these mu mesons weren't mesons at all, but heavy electrons. We then had to look at the neutrinos that were being produced at either end of the track. Now, the theory that was prevalent at the time was that there was a conservation of the number of electrons and the number of muons. And so what this meant was that every muon had a +1, if you like, and every anti-muon or anti-muon neutrino had a -1. So when the pion decayed, it decayed into a muon and an anti-muon neutrino. Now, when the muon decayed into an electron, it had to produce an anti-electron neutrino to balance out the electron, and because the muon was decaying, it also had to produce a muon neutrino to carry on the preserve the number of muons. And so we now had a theory for what this muon was, and it required a second flavor of neutrino. Now, this was all well and good. It seemed to explain what was going on in the detectors when muons were produced and decayed, but nobody was going to believe this without experimental evidence. And that evidence unfortunately had to wait until 1962, when a trio of physicists, Lederman, Schwartz and Steinberger, conducted an experiment that required the newly invented particle accelerator. What they did was they used a beam of particles, a beam of pions at Brookhaven National Laboratory in the US, and these pions were being funneled down a beam, and as they went down the beam they decayed into muons. And the theory is that when they decayed into muons they would emit muon neutrinos, or rather anti-muon neutrinos. Now, these anti-muon neutrinos were just like electron neutrinos. They were incredibly penetrating, so they penetrated through 13.5 meters of ion shielding that was between their detector and the beam line. And what they observed in their detector was that these particles did indeed exist, and they produced muons, and only muons, in their detector. So they established that there was indeed a second type of neutrino, and this type of neutrino was different to the first type, because the first type was shown to produce positrons in the Cowan and Rines experiment, whereas this type of neutrino produced muons. So two different types of neutrino existed. And they had to wait, unfortunately, 20 years before they won the Nobel Prize for this discovery. Now, by the start of 1947, particle physics was looking in pretty good shape. We'd solved the mystery of the strong nuclear force by discovering the pi meson at the start of 1947. The theory about neutrinos was widely accepted, although hadn't yet been proven, as a solution to nuclear beta decay, and the mysterious mu meson was still mysterious, but it was just sort of an add-on to the theory. Nobody was quite sure why it was there at this point. However, by the end of 1947, things were looking a lot worse. And the reason for that was that during 1947, experiments looking at cosmic rays discovered a new, completely unexpected type of meson. And these were named strange mesons. Not just because they were unexpected, but also because, despite the fact that their mass was more than 3 times greater than the mass of the pions into which they decayed, the lifetime of some of them was more than twice the lifetime of the lighter pions. And nobody had any explanation why such a massive particle would live for such a long time and not decay more rapidly. And these particles became known as K-mesons and eventually kaons. But that was just the opening of the doors to the particle zoo. Around the same time, the first particle accelerators started pushing to higher and higher energies, and suddenly particles were popping out of the ether all over the place. Nobody had any clue what all of these strange, weird mesons were, why they existed, or what they were doing, but they were being found. Every time you turned on a new particle accelerator, you could, pop up with a whole handful of new particles. In fact, the situation got so bad, particle physicists were accused of stamp collecting. Experiment was way ahead of theory at this point, and we were finding experimentally particles that the theorists had no clue what they were or why they were there. And in fact, things got so bad that in 1955, in his Nobel Prize acceptance speech, the physicist Willis Lamb decided that while in the past physicists had been awarded with Nobel Prizes for the discovery of new particles, any physicist discovering a new particle now ought to get a $10,000 fine. Things were in disarray. The gates to what became known as the particle zoo were flung wide, and we needed to bring some order to the field. And that is what we will discuss in a couple of videos' time. But before we get there, what we want to discuss is the inventions that gave rise to the particle zoo, the invention of the particle accelerator and its evolution.